Hello everyone. Today, let's take a look at different types of magmatic ore deposits. As you all know by now, ores are rocks with unusually high degrees of element concentration. If you can recall from my earlier video on the fundamentals of magmatic ore deposits, I explained different complex petrological processes that are involved in the petrological evolution of the magmatic systems. However, you must know that despite their petrological complexity, magmatic rocks have a limited range of chemical compositions. For instance, the concentrations of copper in magmatic rocks range from about approximately 50 ppm in ultramafic rocks through around approximately 100 ppm in mafic rocks to approximately 25 ppm in felsic rocks like granites and rhyolites. The reason for this heterogeneity in concentration of elements is not all magmatic processes concentrate elements in similar fashion. Rather, specific magmatic processes in specific geological environments concentrate elements to form ore. John Ridley, in his book Ore Deposit Geology, distinguishes 5 processes of magmatic ore formation. Concentration of ore elements as a result of very low degrees of partial melting, accumulation and concentration of ore minerals in magma chambers due to progressive crystallization of magmas, separation of two immiscible melts in a magma, extreme fractionation during crystallization of magma, incorporation of a mineral that occurs at a specific depth in the earth. The first 4 processes are related to the sequence of steps of magma evolution from melting in the mantle to final crystallization in the crust. One must remember at each of these first 4 steps, chemical partitioning of elements between phases is central to the ore formation. We'll see how the concentration of ore elements takes place as a result of very low degrees of partial melting. One very important thing to note with respect to the partial melting is it results in the higher concentration of the incompatible elements in the melt relative to the source rock. For those of you who doesn't know what an incompatible element is, let me tell you. It is an element that do not substitute into the crystal structure of any of the major rock forming minerals such as olivine, clinopyroxene, orthopyroxene, and depending on depth, plagioclase, spinel or garnet. The incompatible element is also characterized by a different ionic radii or charge than the cations of the major rock forming minerals. Strong concentration of incompatible elements into the small percentage partial melts is central to the formation of ores of a number of trace elements in rare and unusual magmatic rocks such as carbonatites and alkaline silicate igneous rocks. Moving on to accumulation and concentration of ore minerals in magma chambers during progressive crystallization of magmas. The accumulation of ore minerals directly from silicate magmas takes place during fractional crystallization in a magma chamber as magmas crystallize. For example, accumulation of magnetite as a source of vanadium and chromite as a source of chromium. Such fractionally crystallized minerals typically occur as minor or accessory phases disseminated through commonly occurring igneous rocks. However, given specific conditions, concentrated accumulations of these ore minerals do occur in the form of thin layers in cumulate piles of thick layered intrusions. The process associated with such unusual accumulations will be discussed in my next series of videos. The separation of two immiscible melts in magma is the most important process for the development of concentrations of sulphide minerals in magmatic rocks. Sulphide minerals are the minor component of most rocks, and when these rocks partially melt, the sulphide minerals dissolve in silicate melt up to the limits of sulphide solubility. That is, typically a few hundred ppm of sulphide minerals will be melted. and it enters into the silicate melt. As the silicate magmas evolve, the limits of saturation change and some of the dissolved sulphide may become immiscible and separate out as droplets. When there are enough droplets accumulated, they segregate to form a separate sulphide melt phase that crystallizes on cooling. Chalcopyle and siderophile elements, particularly copper, nickel, and Pt, platinum, and related elements, are markedly more compatible in solution in sulphide melt than in silicate melt, and thus will be strongly concentrated in an immiscible sulphide melt. Apart from the silicate sulphide immiscible melt, the other known immiscible melt pairs include phosphorus and carbonatite immiscible melt, and iron oxide and aluminous felsic and anorthositic silicate magmas. Extreme fractionation results in accumulation of ore minerals at the end stages of magma crystallization, that is, in the residual melt, which is significantly enriched in incompatible trace elements. The enrichment is such that the rare minerals that crystallize from the residual melts will have incompatible trace elements as their major components. This is the process that results in genesis of many granitic pegmatites that are the sources of rare metal deposits such as lithium, beryllium, niobium, tantalum, tin, and uranium, and also some of the gem minerals such as emerald and topaz. The last process of magmatic ore deposits is not related to the sequence of steps involved in chemical evolution of magma. Rather, the process involves the carriage of relatively low concentrations from depth of greater than about 140 km in the mantle where the mineral is stable to the surface. For example, diamonds. In the case of diamond deposits in kimberlite and lamproite, the diamonds are transported to the surface by the kimberlitic magma that are generated below the depth of the graphite diamond transition in the mantle. I hope that you got some basic understanding of the different magmatic ore process. Each and every magmatic ore process described here will be explained in detail in the upcoming videos. We shall see the genesis of the RE deposits and carbonatites in my next video. Until then, have a nice day. Bye-bye.